everybody. So today we'll talk about the uh, reactions of alkenes. So before going to reactions, first let's discuss about the stability of alkenes. So as we discussed that if we have cis 2-butene versus a trans 2-butene. So this is the trans 2-butene. So trans is more stable than cis. So cis is less stable than trans. Okay. Why here? Because of the steric hindrance. Big group same side they create steric hindrance. So this is the factor. In addition, more substituted alkenes are more stable. So let's say you have just ethylene. Okay. Ethylene is less stable than propene. Okay, and propene similarly is less stable than butene. Cis-butene. Okay, and this is less stable than 2-methyl butene, and which is less stable than tetramethyl butene. Okay, so this is the trend you should know. Okay. So here, here you can include more this one trans, okay, as well as so this trans is more stable as I have shown than the cis. So this is the stability pattern. So why this is a this is the stability pattern? Because of the hyperconjugation. Okay. So what is a hyperconjugation? Hyperconjugation is the interaction of a filled orbital with an empty orbital. Okay. So filled orbital here, let's say you have, say this is the carbon, okay, and you have here the carbon adjacent if it is substituted, and you have a hydrogen. Okay. So hydrogen, this carbon hydrogen bond, this orbital is full, okay, and then here you have a pi bond, and this pi bond is the anti-bonding of this pi bond is empty. Okay, so what happens, this is a partial interaction makes this stable. Okay, so sigma and pi interaction, so more this interaction will be, more will be the stability. Okay, so remember this hyperconjugation makes this stability. And this stability is determined practically by hydrogenation. So we'll talk later about the hydrogenation reaction. So what happens when by heat of hydrogenation, when we react a pi bond with hydrogen in the presence of palladium catalyst, it forms an alkane. The pi bond is gone. Okay, and this this reaction gives energy in the form of heat. Okay, so here remember, if the reaction gives more heat, means more energy is released. That means the double bond had more energy. Okay, so and if this is so more energy means less stable. So remember, more energy, anything has more energy means less stable. And the reverse, less energy means more stable. So less heat release means more stability. So if we'll go the previous slides, so less stable means if you do hydrogenation, this one, then it will give more energy here. Okay, so this will give more energy than propylene. So it means this is less stable. Similarly, butene will give less energy than propine, and then so on. Okay. So among all these compounds, which one will give the least energy? This 2,3-dimethyl butene will give less energy, least amount of energy. It means it is the most stable. Okay, so another reaction is now come to the reaction first. Electrophilic addition reaction. Electrophilic addition reaction. So electrophilic addition reaction means these atoms are added to a double bond. Okay, and let's take the example of propene. And the reaction is started by an electrophile. Let's say if we add HCl or HBr, okay? Here H is an electrophile, it is delta positive, and Br eventually will become nucleophile. So the reaction is started by this one. What happens? The pi bond makes bond with the hydrogen, and this will go here. So hydrogen will go to less substituted carbon. We'll talk later about this one. So less substituted carbon. So here this hydrogen will go to the carbon. Then the second carbon will get positive charge. Okay? And in the second step, Br minus will add to this. Okay, and it will form CH3, CH here, Br, CH3. So this is the example of electrophilic addition reaction. Okay, so this is the mechanism and the reaction. So first step, the electrophile, second step, the nucleophile, and also keep in mind the orientation of the arrows. Okay, so if you draw an energy profile diagram for this, okay, so E here and here, progress of the reaction. So what will happen that here, suppose the propane plus HBr. So first step will be this one, okay, that energy barrier you will have here, and this is the intermediate CH3, CH plus CH3 and H plus Br minus. Okay, and then the second step will be this bromine reaction, and here will be the product CH3, CH, Br, and CH3. Okay, so this is the product. So this is the transition state, remember. So what happens in the transition state? It is the bond formation between this bond, okay, with the hydrogen. So what happens here? When this bond starts forming, the electron cloud, electron density goes away from this carbon, okay, and the new bond formation starts happens here. So when it is goes away means it start decreasing. This carbon gets positive delta positive charge. So this is the transition state. We can write here. CH3, see electron cloud will be less here, so it will get delta positive, okay, and this bond, pi bond, will start breaking, and the new bond will start forming with hydrogen, and hydrogen bromine bond will start breaking. So what will happen? See this this bond, this side electrons density decreasing, this side increasing, so net change is nothing on this carbon. Um, okay, sorry, it's the reverse. Okay, uh, so what happens? This this is the reverse. So what happens initially, the bond breaking, as I said, starts, this bond will start breaking, and the new bond formation will happen from this carbon to the hydrogen. Okay, so what will happen? You have this CH3 hydrogen. This pi bond is breaking and bond is forming between this carbon and hydrogen, and the bond between hydrogen and bromine is breaking, and the electron cloud is coming on bromine, so its electron density will start increasing. There is no net change on this hydrogen. This side it is decreasing, but this side it is increasing. So on this carbon also there is no net change on the electron density. This side decreasing, this side increasing. But this carbon is electron deficient, so it starts developing positive charge. So this is the transition state here. Okay. Similarly here, what happens in the next transition state here? See this, you have a this carbon carbocation, and then here the bond starts forming, and both the electrons will come from bromine. So electron density on bromine will increase, and on carbon it will decrease. So the positive charge will start getting neutralized. Here the negative charge will start getting less and less. So this is the transition state. Okay, so these are transition states, remember, for the reaction of electrophilic addition. Okay, so why the hydrogen goes to less substituted carbon, and the hydrogen goes to less substituted carbon, and bromine goes to more substituted carbon. So when only one product, when you have an option, let us say this one here. Okay, if you react this one hydrogen Br, okay, so hydrogen and bromine. So when it will react with this, so you have the option that hydrogen can go to this carbon or hydrogen can go to this carbon. So in this case, if hydrogen goes to the less substituted carbon of alkene, then you will have this one here, positive charge, more substituted carbon will get positive charge, okay? And in another case, the reverse, hydrogen goes to more substituted carbon and the less substituted carbon gets the positive charge, okay? So hydrogens, that hydrogen from the acid I'm writing in different color, okay? So which one is preferred, which one is possible? Again, come to the stability. See, when it's carbocation means it has an empty p orbital, okay, empty p orbital of this carbon. Here the empty p orbital of this carbon. So again, this p orbital can be stabilized by this filled orbital of carbon hydrogen, sigma bond. Okay? But this one can be stabilized by many filled orbital of this. See, this side you have 3, here you have similarly 3, and here you have 3, 9. Here it has only one hydrogen. So more interaction, this is called hyperconjugation. The interaction, partial interaction between a filled orbital with an empty orbital. So here the filled orbital is P and filled orbital is sigma and empty orbital is P orbital. So this is the hyperconjugation, okay? So hyperconjugation, this one, it will make sigma versus P. So that's why more substituted carbocation will form. So when the more substituted carbocation will form, then the next step will be the bromine will react here. So this will make carbon bromine bond, and your substituents will be as it is, okay? Here I'm writing those two hydrogens and then the bromine, the hydrogen that came from H. So this is the product, okay? This is called regio-specific. When it goes only in one direction, only this product form, okay? If both forms, suppose this one is 90 and this one is 10, then it's just called regio-selective, okay? Only this one will be regio-specific if both, but this one more, 90%, suppose 80%, this one 10 or 20%. In that case, it will be called regio-selective, okay? Selectively one more, specific means only one. So here is the Markovnikov's rule that says that more for the reaction, electrophilic addition reaction on a double bond, more substituted carbocation will form as an intermediate to give the more substituted product. So it means based on that hyperconjugation, you can say that CH3 plus is the least stable. Why? Because there is no substituent. So the empty orbital of this carbon cannot be stabilized by anything. But if you have a substituent, let's say here, primary 1-methyl group, okay? So it means you have like this hydrogen, hydrogen, p orbital, and you have this is empty p orbital, positive charge, okay? Here you have a filled orbital with hydrogen. So this one. So this will be the stability. It provides stability. So this is less stable than this one. Okay, I have only one hydrogen. Now you have 6 carbon hydrogen bond to stabilize the carbocation. This is less stable than the tri-substituted carbocation. Okay, so tri-substituted carbocation is more stable. So this is the Marconi-Curves rule. Okay, so here the same thing that we talked about carbocation stability. So similarly, we can use add any electrophile to carbocations. Okay, so let's say HCl. Okay, if you have this 2-methyl cyclohexene and you add HCl to this, so hydrogen will go to the less substituted carbon, okay, and chlorine will go to more substituted carbon. Okay, so this is and this is the addition. Similarly, HI, okay, so HI can be added to a double bond. Suppose if you have a double bond here, so HI is unstable. It is generated in situ. In situ means during the reaction by mixing potassium iodide plus H2SO4. Oh, okay. So or H3PO4. So this this when salts like potassium iodide, potassium chloride, or bromide is mixed with strong acid like H2SO4, it generates an acid. Here it will be HI. Okay, and this will react with the hydrogen and it will form a carbocation, and in the second step iodine will react to make this product. Okay, so iodine, this is the product. Okay, so another very important thing that stability. So whenever there is a possibility of forming more stable carbocation, then it will form. So let us see this example. If you have here this one, okay, and you react with HCl or HBr, so what happens? This will react with this. And you'll expect after the addition of chlorine, you should expect this product. But this is the minor product. The major product is this. Major product. Okay. So how it is taking the place of this hydrogen here. So how this one is possible? So let us see the mechanism. So first hydrogen will be added. So you will get the more substituted carbocation according to Marconi-Curves rule. Now here you see this is a secondary carbocation. And here you have a tertiary carbon. So if this hydrogen is transferred here with the bond hydride, that is called hydride, means H with 2 electrons. Okay, so these 2 electrons, that's called hydride shift. So you need to show with the bond migrate. So when it will migrate with the bond pair, so it will form here the carbocation. So see here, this is a tertiary carbocation. Okay? And this is a secondary carbocation. So tertiary carbocation is more stable than a secondary carbocation. So it will form in the reaction, and then this will react and it will form this as a major product. Okay, this is in fact this thing. Okay, I'll give you guys more example. It is not only this one, but for elimination reaction as well, this can happen. So let's say if you have this OH, okay, and this one treated with a strong acid H2SO4. So what will happen? H2SO4 eliminates water, OH, and you can expect that this hydrogen will be eliminated, this hydrogen and OH, and a double bond will form here, plus H2O. But this is not the product. Okay, the major product here is this. This is the product here. So how this is possible? So see, first this OH gets protonated. What it will form after protonation? So this protonation will make OH2 plus the hydronium ion, this type intermediate, and then this OH2 will leave. So what will happen? It will form a carbocation here, and it is secondary carbocation. Then one methyl group, okay, one methyl group will migrate here. So it will generate a tertiary carbocation. Okay. Then from here, water will take this proton and then this. See, remember here you have one proton. So this is that one hydrogen. So this will, the proton will be abstracted and the double bond will form. Okay. So this is the classical example of carbocation, and this is the evidence of the carbocation, more stable carbocation formation during the electrophilic addition or elimination reaction. Another example, it is not just this one. If you have suppose cyclopropane, okay, and then you suppose okay, cyclobutane here I wrote, but that reaction can happen in this as well. So there is a chance of here HCl. Okay, so what will happen? It will take this one, carbocation. So here you have a hydride shift. If you do, what will happen? There is a chance of here formation of tertiary carbocation. But here, because of the cyclopropane ring, okay, tertiary cyclobutane ring, tertiary carbocation formation is not that feasible. Instead, what happens that this bond will migrate, the carbon-carbon bond. Then from a secondary carbocation, it will make a secondary carbocation but the ring will be expanded. That releases the ring strain. Okay, and then so ring strain cyclobutane is not a stable ring system. So here the product will be this as well as a major product. So this is the product formation. Okay, so so that shows the migration, and these type of rearrangements are very common in biochemical reaction that happens in the living organisms. Okay, so next time we'll do more problems in the class, and that will make it more clear.